Lecture 19, Optimizing the Compiler. Well, this is the converse of the previous topic. Whereas before we talked about what the compiler can do for you, now we're thinking about optimizing the compiler itself. So looking inside the compiler and seeing what does it do and why this matters and how we can speed it up. So Dr. Nicholas Nethercote, he's the author of Valgrind, which is probably where you've heard that name before, and his associated PhD thesis, has written a series of blog posts describing how to actually optimize the compiler itself. And yes, I see it says serious on there, and whoops, it's correct in the notes, even if the slide uses the wrong one. In any case, there's a certain observation that compiling Rust can be slow in comparison to compiling other languages. And sometimes that's going to be expected, right? Like when you're doing more work, it will take more time, and there's no getting around that. In a lot of circumstances. However, there's still probably significant room for improvement. So this topic is going to be based on the series of blog posts that were written. They have a couple from 2019, one from 2020. There's also some from 2018 as well as 2016. But we're more interested in the recent ones because there's more interesting stuff to do there. An observation from 2016, and it is anytime you throw a new profiler at a large code base that hasn't been heavily optimized, there's a good chance you'll be able to make some sizable improvements. And so that was an observation from 2016 based on the idea, effectively, that Rust is a great language, said Nicholas Nethercote, and Mozilla plans to use it extensively, but the Rust compiler, Rust-C, is slow, and compile times are a pain point for users, and so that prompted trying to improve it. All right. So, yeah, I mean, the easy stuff has probably already been done, especially in the early days, and the more interesting things have happened more recently, we would imagine. So no PhD in compilers is required for this kind of thing. Nethercote himself describes himself as a non-Rust-C expert, and this is actually kind of good news for you, in that it means that you could, if you wish, improve the systems that you don't design and don't maintain, but you're a user of, and you could submit, here's a change that I think would be helpful, or here's a suggestion. There are lots of ways to contribute to a system, even if it's not something you originally wrote and originally maintained, although they're probably not going to take it real well if you say, this is terrible and I want you to throw it away and start again. The suggestions that you give have to be a bit more actionable than that. Anyway, so like any scientific investigation, if you want to find out what's going on, you need to do an investigation, and investigation requires gathering data. So the approach that we are discussing is the Rust-C perf benchmark suite. And that is, here's a workload that we can execute, and we can use that to make a determination about whether a change has improved or made something worse. And that is combined with profilers, a topic we are coming to soon, to find and eliminate hotspots. That is, places where a lot of time is going. Can we make it more efficient? Can we eliminate something that is not necessary but is taking up a lot of time? That's how we do it. The benchmark suite is run on a website, perf.rustlang.org, and it's got a machine there that will take changes and compile them and see how it went. It's a continuous integration server, as you're probably familiar with, Jenkins, Travis, Circle CI, something like that, and it publishes runtimes. However, it's a little bit impractical to do the feedback loop using the remote server, where you submit changes and you wait for the remote server to compile it and send it back, because for the same reason that you wouldn't want to make a change and then send it off to your CI server for compiling every time you wanted to test something out, you need the ability to test locally. So you'll have a better experience if you run it on your computer, and if your computer that you are running it on is itself reasonably fast. right? The machinery has to be representative of typical use. You don't want to be doing this on your 15-year-old Mac Mini. Not going to be representative. The benchmarks that you get out of it won't mean very much, and the limitations of such a machine are such that you're just wasting a ton of your time. But running it on a machine that you would normally use is better. And like anything else, what we're going to do is make a potential change and benchmark it and see if it improved anything. Now, the change that you make isn't random. You're not just change random things and see if it works. That would not be an efficient route for finding a significant improvement. It would be you have a theory about what you think you could improve, and then you make a change to implement that improvement, and then you benchmark it to make sure that, in fact, your theory was correct and the change that you made was beneficial. Maybe it was, and maybe it wasn't. Acceptable changes in this case don't blow up any benchmarks, so they don't make any scenario dramatically worse, and they reduce runtimes by at least a little bit for at least a few benchmarks. Not every change is going to be a win for every single benchmark and every use case and everything. Sometimes there are trade-offs to be made, but you can't make something hugely worse, and it has to be at least dramatically better in one case or somewhat better in a lot of cases, something, so that people will say this is actually a meaningful improvement and is not just noise, because any change has to be justified. Altogether, between January of 2019 and July of 2019, the Rust compiler had its runtime reduced by about 20% from 20% to 40% on the tested benchmarks. So somewhere between 20 and 40% better on most of the benchmarks. And from November 17, improvements are in the range of 20% to 60% between the original code and the newest version. Keep in mind that if we say it's a 75% time reduction, it means the compiler is 4 times fast. It's 4 times as fast. And so we're thinking about how long does it take to compile, and having, therefore, a lower compile time is better. Right? You could also measure the speed at which things are compiled in other ways, but we're going to just go with wall clock time as a way of making the comparison make sense. Okay, it's important to actually make sure that you have representative benchmarks. If you are allowed to just make arbitrary benchmarks, you could prove anything or nothing, depending on what you set out to do. So we have to make sure that we are going to have a good confidence in our change. And so the benchmarks have to be representative of this is what would happen in real life, to some extent. So there are 3 kinds of benchmarks, and they are real programs that are important, real programs that stress the compiler, and then there are artificial stress tests. Real programs that are important is a suite of 15 programs that are important to the Rust community, and the goal is to actually improve the Rust compiler for the Rust community. So using it to compile actual Rust programs that matter to people is a good way of validating that we're checking the right thing. So the benchmarks include features that are used by a lot of Rust programs, so commonly used stuff, the futures implementation, the regular expression parser, the command line argument parser, all those kinds of things. Although something like command line parser really only affects a negligible part of the total Rust program's runtime, a lot of programs do it, so it makes sense to verify that we are compiling it well and doing it so. The Hello World benchmark is not a real program in the sense that nobody is going to write it, but it is an important lower bound. It gives you a good conception of how long it takes to start up the Rust compiler and run it through all its phases on what is ultimately a trivial program. At the other end of the spectrum, there is the web renderer. It's important to an important stakeholder in Rust. I don't think I need to disguise the fact that the web renderer is important for the Firefox browser, and therefore Mozilla, and that would be a real program, and it would be real important. The second category is real programs that stress the compiler. These are edge cases that perhaps don't behave like most Rust programs, but are important in quantifying the performance envelope. For instance, the encoding benchmark contains large tables. It's used for encoding symbols, fine. I don't even really know how to pronounce this. KECCAK, not sure. Contains a lot of local variables and basic blocks and things like that. And UCD contains large static types that check the non-lexical lifetimes implementation. And then there are the artificial stress tests. And many of these are small programs. There's 18 of them or so. And they are performance regression tests for specific issues that have occurred in the past. And so they might even be named after that, like issue-46499. And it is basically if we observe quadratic or other exponential behavior, it's very problematic if the program size gets large, and so many of the programs here are intended to make sure that there isn't a significant regression in that kind of problem. And we can, in fact, take a moment, if we like, to see the benchmark runtimes for the most recent run. It is here at perf.rustline.org/status.html. I, for whatever reason, can't get this little bar to go away, but minor things. It's linked in the notes if you need, and also in the slides. This has a dashboard. The dashboard is kind of interesting. And so it gives you some information about check builds, debug builds, opt builds, that kind of thing. So debug obviously is going to contain the debug information. Opt is for optimized, and check builds are pretty standard as well. And yeah, we've got like tons of graphs that you could play around with. Sometimes they take a while, but we can see if there were any changes that were added. And yeah, I mean, looking at this graph, we can definitely see that there are some changes to be seen. For example, here on 19th of December, we have a revision hash code 8BB302D34D, and we can also see that we had a significant decrease in there as a couple of patches were committed, and sure enough, it even gives you a little breakdown that says, hey, did you know there's a decrease of 4.33% and a different commit hash. And so, as we can see, on any given commit, it's not always linear improvement in every single thing. Sometimes we see, coercions check gets better here and debug gets better, that kind of thing. But we can also see some graphs where actually things got worse. Deeply nested async debug got a little bit worse, or a lot worse. It's 6.81%. So, on the other hand, externs debug is down. It's variable. It's highly variable. I mean, for most things, we can see it got better so far. But for a few of them, it got worse. And here, issue 46499, which I previously mentioned, it got a little bit worse in debug. Not as big of an increase here in the optimized version. So yeah, it's not always going to be the case that any single improvement is guaranteed to be improvement in every metric in every run configuration. However, the test harness is very thorough. It measures the different kinds, so debug, opt, check. Check has no code generation. And with each of these categories, it does at least 5 runs, including a normal build and some incremental builds. We can see that also mentioned on here where there's an incremented version. So if only this part of the program is changed, we don't have to recompile the whole thing. And in the end, a whole test suite harness run here ends up running the Rust-C compiler about 400 times. And yeah, there's tons of data here that you could totally mine if you were interested in taking a deep dive at it. And you can see everything that you wanted to know and way more. Now, in terms of collecting data, our Rust profiling tools are not that different actually from other tools that we would talk about for other languages. perfstat is used to measure compiler runtimes, and this produces outputs of wall clock time, CPU instructions, that kind of thing, and the website can display them, so we get a very full accounting of it. We will be talking about profiling tools in detail. It has its own upcoming little unit in the course where we'll spend some time on it. There is, of course, also the print line debugging. That's a valid option as well to keep some idea of where time is going, even if that's not necessarily the most efficient way to do it. The Rust compiler itself includes some stuff for profiling. There's a couple of things that it can do with the -z time passes option. It's coarse-grained information for knowing about where is time going in large blocks. It won't be very helpful for finding small things. And there are also other tools that are suggested. Cachegrind is one of them. Its instruction counts are very useful. And also there's DHAT. And it is another profiling tool that we will come to later. We talk about memory profiling, and its goal is to find pathological memory uses. That is, either repeated mallocs of blocks that live very briefly, or mallocs of blocks that live for the entire program lifetime. Anything that isn't sort of the normal expected behavior where you allocate memory, you use it for some time, and then when you're done with it, you can toss it. This kind of behavior is a little suspicious as far as the profiling tool is concerned, so we want to make sure that nothing is really going weird with that. So print line debugging is an option for now, including performance debugging. There's some hints in the blog posts about post-processing the print results. So like we're printing in some standard format to a file, so we can then run a tool on it to parse it later, which suggests that we're counting events, or we're doing a lot of stuff to keep track of events, and it's not just as simple as here's high-level information. It is usually beneficial to have your data be easily comprehensible by users, but if that's not plausible, then by all means, if it's a huge amount of data, do some post-processing. All right, so we'd like to look at a couple of micro-optimizations, cases where we are going to make a small change in the hopes that it makes a significant difference. And I exaggerate a little bit with the microscope, see the 0, it should be a 1 kind of thing, but we're not that far off of it. And each of these scenarios that we're going to talk about is an example of looking through the profiler data, finding something that we think is a hotspot, making a change, and testing it, and hopefully we can learn a lesson or two from whatever we have changed, whether we were successful or unsuccessful. It's good to know whether it worked or not. Okay, so the first thing we're going to talk about is do less work, and we're going to do a small optimization on memcpy. That is, well, we reduce the size of structures so that if it's below 128 bytes, the LLVM backend will emit inline code rather than call the memcpy function. And there are potentially two improvements as a result. One is that there are fewer bytes to move, and also we eliminate the function call overhead. So what do we expect from this? Do we expect that it will work? Hopefully. I mean, memcpy is not itself super complicated. We're just moving a bunch of data from here to there, and there is a threshold at which we would say, look, if you said memcpy and it's 4 bytes, what you actually want is an assignment statement, and it would be very silly to memcpy in that situation. On the other hand, if we have a very large amount of data, then doing memcpy with a loop seems like it would make sense, and therefore, somewhere in between, there's got to be a threshold where we say, all right, it's on on average better to call the function if it's above this size, and better to inline it if it's smaller than that size. And we would have to experiment a little bit to find out where that threshold is. So in this case, reduce the size of file structures below 128 bytes because that's the LLVM threshold for doing it inline as opposed to creating a function call. That is probably related to being able to do it with the largest registers that are available. If you can, if it's going to be done with one of the SIMD registers, then actually if it's 128 bytes or less, we could do it in one jump. If it is going to be a bit bigger, if it's going to be bigger than that, then we'd have to involve multiples of those. If it's going to be a 64-bit type or something like that, maybe we can do it in a couple of dual issue assignment instructions. We'll see. But if it's below that size, then we have one less function call. So changing the structures in the compiler itself to be below this threshold, maybe it works. Does it? Yeah, actually. So that actually does have some benefits. One of the pull request changes on here, and there's actually some links in the notes to the various pull requests, but number 64302 shrinks the obligation cause code type from 56 bytes to 32 bytes by boxing some variants, produces a speed up to 2.6%. Another one, subregion origin, reducing the type from 120 bytes to 32 bytes by boxing the largest variant, speeds up some benchmarks by less than 1%. If you're wondering actually why this caused the memcpy calls to be skipped, in spite of the fact that it's already less than 128 bytes, it's because the subregion origin type appears in a B-tree map, and the tree nodes previously exceeded 128 bytes. Third one, non-terminal, 240 bytes, so this is another type, non-terminal type, reducing the number of memcpy calls, giving a win of benchmarks of up to 2%. And there will necessarily be potential performance trade-off on boxing, so when will it succeed and when will it fail? That is an interesting question to think about. What benefit do we get from it? Sometimes it's positive, sometimes it's none, sometimes it's negative. All right, compiler, I command thee. Then there is the manual application of compiler techniques, and a couple of these things that we've talked about, where we said, look, we want to manually specify inlining, or we want to do specialization, or we want to factor out common expressions. Sometimes the compiler would do these things itself, but it's not always going to, and you may need to hint or coerce it into doing that thing. Perhaps in the future, a better version of the compiler will not need the hint, and that is something that we sometimes encounter in this course where we talk about, we added this compiler hint and it improved things, but then we find out, but now that we're using GCC 9 or something, that hint is no longer necessary because the compiler figures it out for you already. So that's a big old never mind. It feels like we didn't do anything. However, it's in the long run a good thing that the compiler is getting better, and I will have to find a way to live with the annoyance of having to update my example every few years. So here's an example of inlining. Pull request number 64420. This pull request inlines a hot function, speeding up some benchmarks by about 2.8%. This function that was going to be called is indirectly recursive, and LLVM usually does not want to inline recursive functions, but we were able to do this where we created two variants of the function, one marked with inline always for the hot call sites, that is the ones that happen a lot, and one marked with inline never for the cold call sites. Second in the list, number 64500. This PR does a bunch of code cleanups, which helped the performance. It works out by refactoring out some repeated expressions and using iterators instead of while loops in some places. Third one, number 67079, which references a previous pull request, number 64545, in which a variant was introduced of the shallow resolve function that was specialized for a hot calling pattern. That is, if we see that this particular pattern is likely, it happens a lot, we can write a version of it for that. And this PR specialized the function some more, improving some benchmarks by up to 2%. Last one on the list, inline functions on some metadata. This is number 69256, and it is based on the idea of marking with the inline directive some small hot functions related to metadata reading and writing, giving a 1 to 5% improvement across a number of benchmarks. And specialization comes up a number of times, actually, in the blog posts, that there are usually some performance gains to be had by identifying that, hey, there's a common variant of this which wouldn't have as many branches or conditions in it, and therefore it would be easier to just use that. Sometimes addition is by subtraction, in that if you just get rid of a bad API, you could speed things up because it forces people to use the good API, which will work better. And surely if you've worked with REST APIs, you've probably encountered the situation of the lady in this image surrounded by a field full of bad API design decisions, or like, people don't understand how HTTP verbs work, and everything returns 200 OK even when there's an error. In this case, the API that was removed, it's removed in PR number 60630, and it disables slow symbol-to-string comparisons because there's a bunch of type coercions associated with that, and forces the use of a more consistent symbol-to-symbol comparison. Right? That seems like it would be faster because of the lack of type coercion that would be necessary. Then we can talk about do less work. It's one of our favorite optimization techniques, and there's a few examples here. Item 1 on the list is PR number 58210, and it changed an assertion to run in debug builds only. This assertion happened to run a lot, and it was a 20% improvement in one workload. So that really does help. Related to that, there was also in pull request number 61612, removed an unnecessary check of whether a particular symbol encountered is a keyword, for a 7% improvement on programs with large constants. PR number 70837, there's a function find library crate, which, well, I mean, it does exactly what the name would suggest. It finds a library crate. And it did a lot of repetitive prefix and suffix matching on file names stored as path buffers, and the matching was slow because there was a lot of reparsing of paths, because the path buff isn't really designed for that kind of thing. And the PR extracts the names of the relevant files as strings, and so use the matching routine on the strings instead of constantly having to tinker with the path buffers. This gives a win on various benchmarks of up to 3%, which, again, it doesn't sound like a lot, but every time you compile, so it does contribute. And another example of doing less work is that the compiler produces both object code and the bit code that's used for crates. The object code is used when compiling normally, and bit code is used when compiling with link time optimization, and a user is only ever doing one of those at a time. Link time optimization is either on or it's off, and so producing both kinds of code isn't helpful. If the user wants to compile without link time optimization, they don't need the LTO stuff, and if they want to compile with it, they don't need the object code version because they have the LTO version. So making both was just a waste of time and space. Actually doing that was somewhat complicated, and we're not going to go into the details of it, but it yielded improvements of up to about 18%. And one of the things that stands out on that is Nicholas Nethercoat said, when faced with messy code that I need to understand, my standard approach is to start refactoring. it is likely that if it's difficult to understand for you, it's likely difficult to understand for other people, and therefore it would be helpful to others, including your future self, to do a bit of tidying up before you're going to make a big change to alter this and see if it's going to make it better or worse. However, I've told you a bunch of success stories, but some of the changes don't work. Not every time is going to be a success. So some ideas that failed: change drain to use drain filter and compress. It made things slower. Try some invasive changes in data representation, all of which slowed things down. That's making the code more complicated, but also making it slower, and that's not a win. Also in PR number 69332, there's a revert of a previous PR 68914 that changed the U8 to 64 LE function in a way that made it simpler but slower. LE in this case, I think, being a little Indian. It didn't have much impact on performance because it's not a hot function, but for no performance benefit, making it more complicated is not cool. You're just adding a headache to future people who are going to use this code and work with this code, so avoiding that is to your benefit. Making the code simpler is, a goal, but it's not the only goal. All right, so these are all small changes so far. We get a couple of percentage speed up, 2% on this benchmark and 5% on that benchmark and that kind of thing. It's nice, but it's only a start. The more interesting changes are at the architecture level, where we might actually get a more meaningful change, and we're talking about real performance improvement here. There's two of them that we're going to talk about in particular. One of them works and the other one doesn't. I'll let you guess which one of them worked and which one of them didn't. We'll start with pipelined compilation, and then the second one that we're going to talk about is linking. So pipeline compilation, compilers also use this design pattern where we have the idea of doing various steps of the compilation process in parallel. As I previously mentioned, there are things like reading in the files and analyzing the code and that sort of thing, and those are discrete steps, and some of them depend on each other and some of them don't. Now, what we're talking about here is compiling a multi-crate Rust project. So there's a dependency graph for that. These are the crates that are used in this program. And Cargo already launches a dependency after its requisites are met. So if the library we are working with here needs the random library and the threads library or something like that, it will, once it has them, start on the current module. That's fine. What's important here, though, is that there's a certain point before everything is done where Rust's compiler has finished emitting metadata for the dependencies because we figured them all out. We know what we need. Once that's complete, then dependencies can proceed in parallel with the requisites. And that actually constitutes, to some extent, pipelining. It's limited, but it is helpful. And so once we have the metadata here, without pipelining, we would work on library A and then work on library B, and then we could start compiling our binary. With pipelining, we can start on library A, and when we're partway through it, we can start working on library B. And then once all the libraries are complete, then we can start on the binary. The authors of this patch were not 100% sure that this was actually going to work, if it was helpful on code that other people wrote or it just worked in the test scenario that they were working on. They crowdsourced some evaluation of the preliminary version. And what did they actually find? Well, a quick summary of the results is, one, they did not find any reproducible regressions. There were some reductions in build time that some people reported, but nobody was able to consistently reproduce it. It may just be normal variance. Number two, build speeds can get up to 2 times faster in some cases, obviously depending on how many libraries that you depend on. And across the board, there appeared to be an average 10% reduction in build times. The standard deviation seems to confirm that either you would get a significant reduction or a very little one. Again, depending on what libraries you use and how much interdependency there is between them and how many of them there are total. But no significant regressions. So, yeah, specifically the compiler side changes that were required for this were the ability to produce an rlib. This is an archive with object code, compressed bytecode, and some metadata, with only metafiles for dependencies as opposed to the full linkable artifact. And number two, the ability to tell cargo that the metafile is created, which was implemented using a JSON message that was sent from the Rust-C process to the cargo process. On the other hand, the linking one, since we already know the first one worked, we have to know that this one didn't work. And the attempt was to use the LLD linker, and using it on Rust-C itself would take the time linking from 93 seconds to 41 seconds, which sounds like a really big improvement. But if you were running this on the CI infrastructure, so not just compiling on your local machine, but actually compiling it on the build server, linking takes like 20 minutes, which is about 1,200 seconds. A 50-second change is about 2.5%, so it's a reasonable proportion of the total, and it's a larger proportion for incremental builds. However, the change doesn't work because there are some design problems in things other than Rust-C. The Rust compiler itself, there's some comments on the linked issue. The Rust-Lang issue on it is number 39915, if you are curious to read into the details. And one of the problems with it, for example, is there's no macOS LLD linker backend that works. The linker on Unix or Linux has to be invoked through the systemc compiler, and you can only choose the specific linker that you want through your compiler if you have a version of GCC that's version 9 or higher, that sort of thing. So a useful tip for these kinds of optimizations is don't get tunnel vision. That is, look and see what's going on in a broader context and see where you can make a difference in the actual execution of the compiler. So I hope this dispels some myths about how compilers work and gives you some insight into how the compiler is a complex software system like any other, and although it does help you do performance improvements to the code that you've written, helping the compiler is also a meaningful exercise and something where you can spend time, and it benefits your program and potentially programs of others as well.